So on page 114, the first thing it says to do is clean the glass tube. So I already was doing that. So here's the glass tube, just a hollow tube about 1 centimeter in diameter. And you clean it with water, but you don't want the water left behind. So then you get the water out using acetone, which many people know as nail polish remover. And it's hard to get it all out because it's such a long tube. So I'm actually gonna like get some air moving through it so that I get all the acetone out. Normally when we're in class, I tell everybody do this outside so they don't hit each other as they're doing this. And that looks much better. So I could see little droplets a second ago, but now they're gone. Then it says to wipe off my fingerprints as best I can. Of course, I have to hold the tube after this, so you just don't want it to be too messy. The reason you need it really clean is because I'm going to put a gas on one side, so it'll travel. I'll put a gas on the other side, it'll travel. And when the two gases meet, they will form, it's actually a precipitate of ammonium chloride, but it will look like a little white cloud. And if the tube's dirty, it can be hard to see. Now, when I put the chemicals in, I'm going to put them in by soaking a cotton ball. And one thing I have to be ready for is I have to make sure this fits before. I don't want to get this thing soaked with chemical and then find that it doesn't fit and I'm dripping chemical all over the place and making a mess. So I know this is too big. This is way too much. So by pulling it apart into half, if I get the right spot, there we go, that's easier. These two pieces should be better. But I don't want to test it with my hands because I'm not going to pick this up once it's soaked. I'm going to test it with the tweezers that I'll actually be using. And so pick this up, make sure it fits. It does. Make sure the other one fits in the other side because they're not exactly the same. It does, so that's good. Next, when I mount the tube, I need it to be as perfectly horizontal as possible. Because if the tube was like this at an angle, the gas up here would go too fast because of gravity helping it, and the gas down here would go too slow because of gravity making it tough. So I'm going to put it in here, clamp it. That's good. I'm going to test to see how level it is with this little bubble level, like you would when doing like hanging pictures or doing carpentry or something. I'm just going to set it on here. And I got lucky. It's pretty darn good. I'll show you with the camera. It looks like that. And if I can get rid of the glare, you should be able to see the bubble is darn close to the center. It's so close, I'm not going to bother messing with it. If I mess with it, I'll probably not get it that good again. So that's close enough. And I'm going to move everything to where we need it. And the camera too. Okay. That's pretty good. So over here, I've got the hydrochloric acid, 12.1 molar, so that's full strength. Over here, I've got, the bottle says ammonium hydroxide, but anytime you have ammonium hydroxide, you also have ammonia, and that's what I need because they're in equilibrium. So this is fully concentrated. Just out of curiosity, I'll tell you, this is 14.8 molar. This is 12.1 molar. I've got my cotton balls ready. I also have a tweezer for each side ready and a rubber stopper. The rubber stopper does two things. Once the cotton ball's in, The rubber stopper minimizes how much gas comes out into the environment. It also prevents the cotton balls from being pushed out. If you put the two cotton balls in and you don't stop them, as the gases start to travel, they might push the cotton ball out of the tube and ruin the experiment. Now, normally, this takes 3 people. One person holds this steady so it doesn't fall. One does the acid side and one does the ammonia side. And we want both of these to be put in at exactly the same time, and that's where we start our timer. I don't have that luxury, so I'm just going to do it as fast as I can. And once both things are in there, I'll start my timer. You can time too if you want. So let's do this. Now, you don't really see anything come off of the ammonia, but it smells really bad. If I wasn't in the fume hood, it would be pretty funky. It also doesn't like to go into the cotton ball. So I'm going to soak the cotton ball pretty good with this. Get a little more. That's good. I'm going to cover it and just let that wait while I get the other one ready. Now, when I open this one, you probably will see a bunch of vapors coming off. This is really nasty stuff. You don't want to breathe it. Like that. You can see it because of the black background. Same idea, except this one's almost empty. I'm going to soak this cotton ball here. Yeah, that's good. Put that lid on. All right, it's showtime. So I'll take this cotton ball here with the acid, try and gather it up a little bit so it's not too much of a mess. Put it in here like that. Put the other one in like this. Start the timer. Put the rubber stoppers in so they don't fly out. You probably see all kinds of crazy stuff going on over here. It's very Harry Potter on that side. The reaction usually takes at least 3 minutes. So while I'm waiting for it to happen, I've got a box of paper towels already soaked with water, ready to go. Because I read the lab and I'm prepared. And I'm just going to take this one and just kind of cover this up. That's kind of fun. If I puff like that. And not keep doing what I just did. I'll also put one over here. You don't see anything over here, but it is still giving off some pretty nasty stuff. I'm going to wash these so they don't get too corroded. I'll be right back. Okay. And I can deal with the rest of the cleanup later. So what's going on here is the ammonia gas, NH3, is wiggling its way that way. The HCl gas is wiggling its way this way. But they're not going at the same speed. The smaller gas will move faster than the bigger gas. So if you look at their masses, NH3 and HCl, you'll find that NH3 is the lower mass gas, so it's going to move faster. So when these two gases meet, they will not meet right smack in the middle of the tube. This one's going faster than that one, so they'll meet somewhere over here is where we'll see the cloud. And it'll start out as a very faint ring inside of here. It'll be a ring on the edges of the inside of the tube. And it'll probably be hard for you to see, but once it's developed, I'll bring the camera in a little closer. And we probably have about another minute before we even see it. Interesting enough, it's this exact lab as to why I have the fume hood. There are other times the fume hood's nice, but this is actually the main inspiration for it, is this exact experiment. All right, that's also why I have this black paper here. Trying to see the white cloud against a white background's tough, so I had to put this up a couple years ago to help out. No, I don't see it yet. Once I do see it, I'm going to make a mark on the glass with this. This is called a China marker or a grease pencil. And it's basically like a crayon, so it'll write on glass a little bit. And I do see it. So we can stop the timer. I'll tell you what it is. So I got a time of 3 minutes and 42 seconds. I want you to put that in the data table. The data table is on page 116. And put that in seconds. So 342, so multiply 3 times 60 and add 42, and that will be your seconds. I'm going to make a mark as to where I see the little ghost. And then I'll bring the camera in and see if I can actually get you to see it. The glare makes it really tough. Let's see if I get rid of the glare. Try turning this off. No, that's not turning out very good, is it? See, the little ring knows that I'm recording this time, and so it's not wanting to be helpful. Let's see if I bring it up and go at an angle, and maybe you can see it a little better then. But you have to be careful. Don't mistake the glare. So as I do it like this, you should see a little white ring right about there. You might also see a black mark. That's where I made the mark of where the ring first appeared. And the ghost is right there. I call it the ghost. So a couple of things that are happening right now as I've been waiting. First thing that's happening is the ring is getting pushed that way. It doesn't stay where it originally formed because the ammonia gas is still moving faster that way. And the hydrochloric acid gas, HCl, is moving this way but slower. So the ring's getting pushed to the side. Sometimes it gets thicker. It's not doing that this time, but it is settling a little bit. So at the bottom of the tube, there's extra precipitate that's kind of fallen down. And that'll just keep going on. If I just let this sit for maybe another 10, 15 minutes, when I come back, there'll just be a whole bunch of this in there. So we'll do that. We'll talk a little bit. We'll come back and see if it's actually collected enough for it to be really obvious. All right, it's now time to talk about the calculations. So it talks about a distance. So what I need to do is measure the distance from where the HCl started to where it reacted, and the same thing for NH3. So I'll do that now. This was the NH3 side. So from where I made my mark, it's 347. So 347 millimeters. That goes where it says distance from NH3 end. And I'll do the HCl now. Yeah, 228. So that one's 228 millimeters from the HCl. And that makes sense. It makes sense that the NH3 moved farther because it was moving faster before they met. Now in the calculations, if you flip to the next page, well, you don't have to flip, but just go to the next page, 117, you'll see Gas Lab 2, and the relevant questions are 3 to 5. 3, when you calculate the velocity, that's just a typical velocity. It's just distance over time. You can leave it in the units it's in. 4, determine the ratio of velocities. Please do the ratio as it says. Put your speed of, or velocity of HCl over your velocity of NH3, and then do the math. Don't leave it as a fraction. Actually calculate it and get what the decimal is. This is going to be your experimental value because it's from the data. Question 4.5 is just a mathematical proof. So to help you with this is on my handout. So in the old Google Classroom, if you go to yesterday's class, you'll see it says Gas Lab Prep. Click on that sheet. And then on that sheet for part 2, you'll see 2 equations that are circled. The first equation that's circled is our traditional Graham's law, m1v1 squared equals m2v2 squared. I've just replaced the 1s and the 2s with the relevant gases. What I want you to do in question 4.5 is show me mathematically how you go from the first circled equation, the normal one, to the second circled one. You don't use any numbers, just do algebra and show me how we get from one to the other, because this is going to help you understand why question 5 will work. In question 5, your experimental value will be the velocity of HCl over the velocity of NH3, which you already calculated in question 4. Your theoretical will be based off of the molar masses of the gas. And you'll see in my equation, that's the square root molar mass NH3 over molar mass HCl. Notice that they are now inverted. And that's part of the math I want you to show me. You'll see why that happens. And then you'll do your percent error for number 5. We'll see what period did best. Even though I did it every time, I'm sure one will come out better than the others. Let's actually go back to this. Let me grab this and bring it over here, or I'll just move the camera and see what it looks like now just for, I'm going to bring it over here. And I'll put it right here. Let's see if I can show you all the cloud that's formed inside of there. Like that. Boy, the glare is just horrible. It's hard to tell what's glare and what's not glare. Maybe if I cover it up. Yeah, that helps. If I get rid of the glare, you should see a bunch of cloudy stuff that's kind of settled in the bottom of the tube. Like that. And the edge of the cloud is actually moved all the way over there. That's where the new edge, that's where it started, and it's been pushed over there by the ammonia. I'll put this back so it doesn't stink up my room, and I don't want to smell acid vapors.